Hello, this is Team Katara presenting AI4Agile for Jira. The team consists of Phong, Bach, Emily Cawlfield, Nain, Galvan, and Aric Monary, all from Washington State University, Everett, USA. AI4Agile is a Jira cloud app which accelerates the user story refinement process in agile development via artificial intelligence and visual aids. Jira, the platform our app is integrated into, is an issue tracking software developed by Atlassian, which offers bug tracking and agile project management. Jira software has two main system versions, of which our app is specific to its cloud service.
Our project addresses these core requirements of the AI4Agile proposal, giving user recommendation from epics and user story, as well as a visualization tool to showcase the relationship between epics, user story, and tasks. We also integrated our application to the Jira platform.
Our user story refinement is comprised of three processes. First, epic decomposition takes an epic and breaks it down into large user stories. Then, story optimization splits user stories into smaller stories when possible. Lastly, task generation creates stories from the created user stories. We modeled our automated user story refinement processes off of a manual refinement as seen in Figure 1. It was found that all processes relied on clustering around keywords as highlighted. Additionally, the level of focus on details grew as we progressed through the refinement processes. And now we'll move on to the demonstration of AI4Agile. In Jira, all items are considered issues. Epics are purple, user stories are green, and tasks are blue. All issues can be viewed through a variety of different ways, but for this demonstration, we'll be focusing on the roadmap. To begin the epic decomposition process, we'll first select an epic. From there, we'll select the epic decomposition button that will then automatically populate with 5 user stories. From there, we can select the number of stories we want to create, right for more, left for less, and then we can refresh in order to generate the number of stories we selected. From here, we can either edit or we can select the stories that we want to create. So we'll create these first 2 stories, and in order to view them, we'll either need to refresh the page as Jira Cloud inconsistently loads newly created stories. Here we can see our newly created stories. And from here, we can also see that these newly created stories have a blocking relationship with the epic that they are derived from.
This user story we have here is a little bit too big. We can use a story optimization tool to break them down into smaller stories. We can start the process by clicking the story optimization button, and it will load up our panel. We can drag our slider to the left or to the right if we want them to be less connected or more connected among the individual sentences or components inside the story. Then we reload our suggestion. Now we have 3 options, so I will choose these 2. Create, and then we will refresh our browser to see our newly created issue. Now we can see that 2 new stories are created. The original will have an optimized tag right here. The objective here is that our application won't delete or overwrite your currently existing story. Besides that, our newly created also show the optimized tag and the blocking relationship.
Task generation, you first want to make sure you have selected a story. This is depicted by a green icon shown on the left. Next, you want to click this task generation button. This will bring you down to this panel shown here. This panel shows all the tasks that can be created from this one user story. Next, the user can click a task that they want to create, and if the user doesn't like the specific task, they're able to edit it. Now click this create selected button and refresh the page. As you can see here, the task has been created. This is depicted by a blue icon shown on the left, and you can see the issue that blocks it, which is the user story that it was created from.
The purpose of the dependency visualization graph is to help Scrum Masters assign tasks or help developers wanting to see which issues relate to one they were assigned. Each of the 2 graphs show epics, user stories, and tasks by their issue keys, and some explicit and implicit relationships between them, such as blocking, hierarchy, and issues assigned to the same developer. Explicit relationships can be manually input via Jira's linked issues field, or are present in the hierarchy, such as this task is derived from both a story and an epic that is underneath. To look at more details of an issue, we can click on it to be taken to its specific issue view page. And implicit relationships are shown in the developer cluster graph, making it easy to see at a glance which issues are assigned to which developer, including this group here, which have no one assigned to them.
AI4Agile is made up of 3 web applications. A Node.js web app acts as the front end that is served to users in the Jira user interface, and it communicates with the back end using Ajax. 2 Python web apps act as the back end and receive requests from the front end using Flask. Each back-end web app hosts features respective to either story refinement or dependency visualization. Initially, the app was hosted locally using NPM for development, but was transferred to be cloud-hosted with Microsoft Azure for customer evaluation.
Beside the team, we enlisted the help of several faculty and industry mentors, Dr. Bolong Zeng, Jeremy Thompson, Dr. Hoa Khánh Dam, and most importantly, Skip Barkers, who serve as our domain expert, mentor, and client.
For communication, we use Microsoft Teams. For task management, we use Jira software and Microsoft Teams. Our repository was on GitHub. For documentation, we use Google Drive. For cloud hosting and development, we use Microsoft Azure. Our agile and iterative development is shown on Figure 3.
We went through many software engineering phases for several iterations. In addition to the development, we recognize that the score competition emphasizes on the software engineering process just as much. And here are a look into our approach for the requirements, design, and testing phases. First, we model the requirements using Chaos Model, a goal-oriented requirement engineering tool that emphasizes goals in requirement acquisition. Using Chaos Model, we want to guarantee thorough traceability across all requirements, which includes in describing the problems, identify top-level goal to address problems, and stating the constraint for the solutions. On the right, Figure 4 show our top-level goals, and Figure 5 show the first level of functional goal. We obtain the requirements after breaking this goal down and refining this model. After that, we met with our professional mentor Skip Barkers to get direct feedback to revise our requirements. The weekly Scrum meeting with our professional mentor client, such as Skip, helped us tremendously to get a frequent feedback and clear vision on the project requirements to ensure effective use of our time.
Our team's design choices. UI and UX design decisions. We use tooltips shown in Figure 7 and integrated processes versus pop-out windows shown in Figure 8 to follow Jira paradigms. We use Atlassian user interface library shown in Figure 7 so our buttons will look out of place in Jira. We use suggestions list shown in Figure 6 and select and deselect all buttons shown in Figure 7 for ease of speed. We also analyze the impact of adding new steps or buttons to lessen learning time. Epic decomposition was initially implemented 3 different ways. The benefit of these ways allowed for a dynamic selection of clusters. A limitation was a large amount of noise meant that useful clusters were unable to be identified. The revised implementation used TD-IDF and k-means clustering. A limitation is that it required user input. For story optimization, it was initially implemented using Google Word2Vec model and SIF. A limitation with this is that it was computationally intensive. The revised implementation uses TF-IDF, cosine similarity, and function decision. The benefit of this is its speed. For task generation, it's currently implemented using standard library. The main goal is to create simple sentence from reducing compound or complex sentences using parse speech tagging and enhanced word dependency. Limitation with this is that it doesn't give you the best dependency results, leading to bad simple sentence creation.
The verification of our application was fulfilled through constant consideration of both the functional and non-functional requirements that were created through the chaos modeling and requirements elicitation. The requirements were considered during the design and implementation of components. Validation was facilitated through our industry mentor, who served as our customer. A large portion of both validation and testing were done through direct observation with our industry mentor. Overall, the requirements, observations, and feedback were used within the iterative development flow seen below.
Continued work on this project post-competition would involve making AI4Agile available on the Atlassian marketplace, which includes adding security measures and providing documentation pages. Aside from that, refinements would be made to the components themselves, including optimizing the UI flow, as can be seen in the example on the left, adding tooltips or keys to the graphs, and improving the text process outputs. Looking back on this project, the team thrived when meeting often and having collaborative work sessions, and assigning specific people to different development areas, one of the many helpful tips from our subject matter expert and mentor. Doing this over again, we would set up continuous integration and deployment early on, and change how much or little time we scheduled for certain phases. That's AI4Agile. Thank you for your time. your time.
Okay, we're live. Thank you very much for that lovely demo. We have I think it's 4 of you here from Seattle, right? Thank you very much. We're going to kick off straight away with Fernando Castro. Thank you very much, Castor. Questions, he's been very efficient. We have them already in the chat. So I'm going to start. I understand AI4Agile identifies the relationships between tasks using clustering. Did you, the authors, experiment with supervised methods? Have you noticed false positives, cases where a relationship that should not exist is identified? And I think we have Aric going to answer that one. Thank you, Aric.
Yeah, so our initial approach to AI4Agile did involve exploring supervised methods. However, that does rely on a training set of data. There are larger projects that do have that historical data to train models off of. However, a criteria for our application was that it would be universally applicable to all projects, which means projects that don't necessarily have that historical data to train a model off of. Additionally, we did not want to create a universal data set because all projects are unique in their own way, and we didn't want to train a universal model for all types of software development projects. So we ultimately ended up just using clustering methods, as that would not necessarily rely on the historical data and would be very specific to that project with its data. We did notice in a few of our different processes, like our task generation, for example, that we do have some false positives in terms of the way it does break down the user stories into the tasks. Additionally, the ways that the story optimization or the epic decomposition breaks down the relationships or breaks down into user stories are also a little bit sometimes inconsistent or not what the user would desire. However, in our application, those are editable, so they can be changed accordingly.
Thank you very much. Quickly on the next. The example.
I can add it to the first questions.
Yeah,
So
okay.
yes, so talk about like the uniqueness of each project. We also try to using the data from all the projects to train our algorithms, and after we experiment with a few ways to generate like new sentences using the old data to see if we can generate like a new task or a new optimized story that can like be meaningful. And after like multiple like try, we decided that like the new generated data is and they were like remotely closely related to what we want to achieve. So that's why we wanted to go with the clustering, which is a more efficient way to generate new story in tasks. Yes.
Okay. You're happy with that, Fernando? The answer? Yeah. Okay, quickly with the second one. The examples in the video are illustrative and easy to follow. However, they follow a pattern where in most cases there is a direct relationship between sentences in the stories and tasks. Have the authors experimented with more complex stories? For example, comprising a single sentence but ideally leading to multiple tasks? If so, what did they find out? If not, why not? And I think Nain is going to answer this.
Okay, so so the one thing about the task generation that sometimes not complete sentences are created from a user story. So as shown in the demo, that we're able to edit that task if the user doesn't like how it is. And we didn't really experiment with compromising a specific user story to see if a bad sentence identified, because sometimes that just happens based on the algorithm. So it's kind of hard to determine which specific sentence causes that.
Okay, thank you. And the last question. Are you okay with that, Fernando?
I'm going to make a quick question using voice because it's faster.
Yeah.
Testing of this system, have you seen big sets of dependencies between tasks, and did they give you any trouble?
So for tasks, it wasn't really created based on
dependencies or like clusters, like the user stories or epic,